Hello, this is MA280-Multivariable Calculus. I'm Professor Wheatley. Today's topics, lines and planes in 3-space. Okay, so we're very used to seeing lines in the plane, i.e. two-dimensional space. And we know that one way to get a line in the plane is to have 2 points on the line. Alternatively, though, what 2 points on the line do is allow us to actually have a point and a slope. And that's the definition we're going to use to derive lines in 3-space. So lines in space, which of course we know means 3D, just like in 2 dimensions, determined by a point. And in 2-space, it was a slope. Well, here we have a vector giving the direction of the line. And even though the line goes in both directions, the vector gives us essentially the slope or the tilt of the line. So we have a vector giving direction of the line. So let's draw a little picture here. So there's x, y, and z. And there's our line L. And it has some point that we know on the line. Call it P0. And then we'll put another point on the line up here. And maybe down here, we know some vector that runs parallel to the line that gives the direction of it. Okay, so what's a line? L is a line in space, and the point we know is P0, which has coordinates x0, y0, and z0, and it runs parallel to some known vector v, which has components v1, v2, that should be a j, 2j, and v3. Okay, so there's your line in space. What is the line definition-wise? Well, L is the set of all points P with coordinates x, y, z. So all these points along the line, other than P0, are some point P that we care about. There's a set of all the P's that lie on that line, for which the following is true, for which vector P0P is parallel to V, right? So vector P0P is this vector right here. It's certainly parallel to V, all right? And what does that mean equation-wise? Well, remember that 2 vectors are parallel if they're scalar multiples of each other. So it means that vector P0P is equal to some scalar multiple of V. So i.e. TV, no pun intended there, for some scalar t, and we allow t to range through all real numbers. So again, this line is infinitely long. It goes through all real numbers. And every single vector, every single point P on the line is some vector from P0 that's a scalar multiple of V. Okay, so let's examine this a little bit further algebraically. Let's give ourselves some room over here. Okay, so what we have the equation P0P equals TV, right? And we can break these things down. We know what P0P is and what TV is. So P0P is the distance from P0 to P. So we have this usual vector components of the components of P minus the components of P0, Z0K, as such. There's the left-hand side. And the right-hand side, well, we know what the vector V looks like, and it has the components V1, V2, and V3. So there's the right-hand side. No surprises so far. And then the goal is sort of combine things and make them look nicely. So what we're going to do is we're going to get all the just x, y, and z terms, the unknown terms, the variable terms, if you will, on one side of this. So we have an xi, a yj, and a zk. And then all the known terms, I mean, remember, we know the value of v1, v2, and v3, and we know the value of x0, y0, and z0. We know those values. So we're going to kind of cluster all that junk on the other side. Y0j plus z0k. And we still have all that stuff. So I'm just bringing down the stuff from above. So all of our known terms are over here on the right-hand side, and our unknowns are over here. And so what does that give us in the end? Gives us, if we call this left-hand side r of t, something that depends on t there, what we get is a vector equation where r0 is equal to the vector x0, y0, z0. So what I'm doing is I'm just saying, okay, dependent on t over here, and from some starting point here, and we add on some scalar multiple of this vector v, we're going to get out some position on the line. Okay? So this is a vector equation. So this is a vector equation for the line L through P0, X0, Y0, Z0, parallel to V. And again, T can range through all real numbers. The line goes infinitely long in both directions. So it's R of T equals R0 plus TV, and we let T range through all reals. Okay? So that's the vector equation. However, what may be more useful to us than the vector equation are the parametric equations for the coordinates of the line. So parametric equations for the line. Remember that what we're talking about here is defining each coordinate x, y, and z in terms of the variable t. So parametric equations for the line, well, they come directly out of this by just looking at, well, what is the I component on the left-hand side? Well, it's x. And what is the I component on the right-hand side? Well, it's x0 plus tv1. Same thing with the y component. On the left-hand side, it's on the j component, I'm sorry. On the left-hand side, it's y. On the right-hand side, it's y0 plus tv2. So these equations come directly out of our above statement. X is equal to x0 plus tv1. Y is equal to y0 plus tv2. And z is equal to z0 plus tv3. And that should make sense. We're starting from some initial point on the line. We're moving some multiple of v in each direction. There are your parametric equations for the line. Okay, let's look at an example of this for a minute. So, example, let's find parametric equations for the line through 2 points. So just like in 2 space, 2 points determine a line. That's no different. Through the points 2, 1, 3, and -1, 3, -2. Okay, so let's find the equations for this line. All right, well, we've got to have a point on the line. Well, hey, we've got 2 of them. That part's taken care of. Got to have a vector parallel to the line. Well, certainly the vector PQ is part of the line itself, so it's parallel to it. It's actually in the line, so that works. So if we get the vector PQ, let's see here. What do we end up with? -1 minus 2i plus 3 minus 1j plus -2 minus 3k. All right. And that gives us -3i plus 2j minus 5k. Is that what I've got here? Good, it is. So this is certainly parallel. So this is parallel to the line. And again, it's even more than parallel, really. It's part of the line, but it doesn't matter. Parallel vectors are positioned easier regardless. Use either point as your P naught. You can use P, or if you like Q, you can use Q. So you can choose P as your P naught, but again, Q works just as well. No problem with that. And so then it's just plug and chug. We have our X naught, our Y naught, and our Z naught. They're coming out of the points of P. Our V1, our V2, and our V3 are coming out of the coordinates or the components of our vector. So X is 2 minus 3t. Y is 1 plus 2t. Z is 3 minus 5t. There you go. Okay. Now, what we can do now, if we'd like to, is now that we have equations for the line, we can get any point on the line that we like by just plugging in various values of t. All right? Let's make some room over here. So we can get any point on the line by choosing various t values. Right? So for example, if I like t equals 2, so e.g. t equals 2 yields the point x equals 2 minus 6, which is negative 4. Y equals 1 plus 4. I'm just plugging in t to these equations down here. Nothing fancy going on. Y equals 5. And z equals 3 minus 10, which is negative 7. So the point negative 4, 5, negative 7 is on the line. Okay. All right. Well, it's not so very different if we would like to parameterize a line segment also. That has no problem with it. All right. So we can do the very same thing. Essentially, only we need to restrict our t value so we can parameterize a line segment also. And the only difference here is, well, a line segment doesn't go on infinitely. It has a finite starting and ending point. We need to figure out the t values that correspond to those points. Okay? So we need to find t values for the endpoints and restrict t between these values. Okay? You need to find t values for the endpoints and restrict t between those values. All right, so why don't we go ahead and parameterize the line segment between the same 2 points. Let me come over here and get rid of this, and we're going to change our problem really only slightly. So let's change the directions up here, and we'll leave the same point up. So let's parameterize the line segment between these 2 points. Okay? And so we have the equations already. I just erased them, but we can write them again, certainly. Y equals 1 plus 2t, and z equals 3 minus 5t. Right? Those are from the same example we just did. And so now the question is, well, what t values correspond here? Well, luckily for us, we don't need to be too creative with a lot of these problems. That were designed to work a certain way. So when t equals 0, well, what point on the line do we expect to end up at? Well, clearly the starting point, the initial point. So when t equals 0, x, y, z is equal to 2, 1, 3, which is p, right? I mean, that should make sense because we started off at this initial point here. These values over here, these v1 and t's, were based off of a vector starting here, okay? And when t equals 1, well, where do we expect to end up? Well, we're traveling from p to q. That's our vector we want to get anyway. So we should end up right at q, and we do. And we wind up with a -1, 3, and -2, and we do get q. When you plug in 1 here, you'll get q out again. And so our parameterization is just the same as before. So it's the same exact equation, so it's the same parametric equations with the restriction 0 is less than or equal to t is less than or equal to 1. And that will keep us stuck between those 2 points only on the line segment. Okay. So let's shift gears slightly and talk about how to determine distance from various things in 3 space. Well, we know the distance between 2 points already. We know that formula. That's the same thing as the 2D formula, except it has the extra z term into it. Let's talk about, here's a mouthful, distance from a point S to a line that goes through point P parallel to vector V. That's a lot of writing, but what is it saying? Well, I'm asking how do I get the distance from a point to a line, and I'm just specifying which line I'm referring to. I'm referring to the line through point P that runs parallel to vector V. Okay? All right, so I'm going to present the following without proof, though the derivation is in the textbook and in most books, if you don't have the Thomas book that we're using for this course. So there is our distance formula, and again, I'll present that without proof. So it is the length of the cross product of PS and V over the length of V. All right, so we can go right to using this sucker then. So let's find the distance from the point 1, 2, 1 to the line L, and I'll give you the parametrics here, 1 minus t, y equals 3t, and z equals 2 plus t. And this point does not lie on this line. Certainly, if it did, the distance would be 0. It would be a redundant question to ask. Okay, so let's come over here and get some room to work. All right, so L, well, to talk about L, basically we need a point P and the vector V, and we have the equation to the line. We have to go backwards now and get a point on the line and the vector parallel to it. Well, that's fine. A point on the line is not hard to get. Any value of t will work for that. So L, where am I here? L passes through the point P102. And how did I get that? Well, I plugged in the easiest t value I can think of, which is 0. You plug in t equals 0, you get exactly those values out. But if you don't like 0, if you have some aversion to it, you can use any t value you want, get any point on the line. That's easy enough. Okay? And it's parallel to which vector? Well, the vector is -I plus 3j plus k. And remember, the coefficients of t in these parametric equations down here, they are the components of vector v. Okay, so -1 here, 3 here, +1 here, they're the components of our vector v. All right? So now we have that. This is just the coefficients of t. That wasn't too terrible. We need the vector ps. Well, that's pretty easy. We have p. Where's s? S is over here. So what have we got here? We got 1 minus 1i plus 2 minus 0j plus 1 minus 2 k. And let's see here. Am I going in the right direction here? Yes, I am. So that would be 0i and 2j, and 1 minus 2 is minus 1k. Right? Minus 1k there. Okay. So now we need to figure out what the cross product is and do it over the length that way. So let's go ahead and do it right down here. So we need PS cross V. We'll set up our determinant. ijk. PS is 0, 2, and -1. And V is -1, 3, and 1 as such. And then let me just erase this and let us work longwise across here. We'll leave the formula up here, though. Okay. So what is this here? This is I times the 2 by 2, 2, -1, 3, and 1, minus J times the 2 by 2, 0, -1, -1, and 1, plus K, 0, 2, yeah, it looks kind of like it's in the matrix, doesn't it? 0, 2, -1, and 3. So there's our determinants. We're used to this by now, hopefully. Okay, we'll work this out here. So this is 2 times 1 minus -3 is a positive 5i. Let's see, 0 and 1 is 0. That's positive 1. So we have a -1 times a negative j should give us a positive j. Is that right? 0 minus 1 is -1 times, yeah, positive j, that looks right. And then 0 times 3 minus a -2 is 5k. Okay. That looks right to me. All right. Actually, that's not true. No. Because 0 times 3 is 0, so this would be minus -2, which would be positive 2k. Yeah, that looks better. Okay. So I got good. All right, so there's our cross product. We have enough information now to fill in the distance formula. We need the length of PS cross V, which is, 25, and 1 is 26, and 4 is root 30. So there's root 30. And the length of V, where's V? Here's V. So it's 1 and 9, and 1 is 11. So this is root 30 over root 11. And that's about 1.65. So there is the distance from that point to this line. Okay. So enough about lines for a minute. Let's go to planes. Let me make some room to work here. So if lines are kind of what we think of as the fundamental object of 2 space, well, planes perform the same task more or less in 3 space. And if it takes 2 points to define a line, well, probably guess if we wanted to, it'd take 3 points to define a plane, and we'll see why that's true shortly. So, equations of planes. Equations of planes in space. Of course, it makes no sense to talk about planes in the plane. There's only one plane there. It is the plane. So what determines a plane? Well, I said 3 points, but more than that, they're determined by a single point and a vector which is normal. Of course, normal to us means perpendicular to the plane. So planes are determined by a point and a vector normal to that plane. In other words, if we know something that's perpendicular to a plane, we know its tilt, and a point will give us the position of it. Okay, so let me draw a picture here first, then I'll put the words down. So we usually draw planes as these kind of parallelogram-looking things. All right. Well, here's our point, P0, and some other point on the plane up here, which we'll call P. And here's our normal vector. It doesn't look that normal, does it? We had an abnormal normal vector there. All right. So there's a normal vector pointing straight up out of the plane, perpendicular. And so what is this thing? Well, plane M passes through point P naught, and again, we'll give it some coordinates, x naught, y naught, z naught, and is normal to vector n equals ai plus bj plus ck. And I'm not specifying that the normal vector has to be a unit normal. Doesn't make a difference, really. Any normal vector will do. And so then, what are these points P? Well, or what is M in terms of equations? M is the set of all points P, x, y, z, such that P naught P, that vector, from P naught to P, is orthogonal to n, right? Because any vector that lies in the plane, n will be normal to it, therefore any vector will be orthogonal to n. Okay? Well, what does that mean equation-wise? Well, remember that a big check we had for orthogonality was the dot product. And it means that n dot P naught P is equal to 0, right? Two vectors are orthogonal if and only if their dot product is 0. Well, there you go. Okay, let's examine that equation more closely. Let me come over here. So we have this equation that's not that useful to us quite yet. N dot P naught P equals to 0. Well, we know about n and P naught P, so let's go ahead and fill things in. We know n is ai plus bj plus ck, and we're dotting it with P naught P. So remember, P naught P is x minus x naught I plus y minus y naught j plus z minus z naught k. Is that what I have? Yeah. And that's all equal to 0. And I guess we ought to, well, we don't need any room. I think we can go down there. So now, what am I going to do? I'm going to gather all of these terms together. So the dot product, remember, what that meant was the coefficients times each other and then add the sum, or get the sum. So this implies that A times x minus x naught plus B times y minus y naught plus C times z minus z naught is 0. Right? There's the dot product of those two vectors. And just to make things look a little nicer, I'm going to kind of do a catch-all constant term. Ax plus by plus cz equals d. And d will be our catch-all constant term. I would have had an ax, or a negative ax naught, and a negative by naught, and a negative cz naught hanging around. Those are all constants because I know the values of all those things. I'll put them all into d just to make life look a little easier for us. Make these equations a little less daunting. And that's plus and plus because I moved them to the other side. So I moved all the negative terms over here to get d. So there is your basic equation for the plane. There's your constant. Okay? All right. Well, let's try to figure an equation for a plane through 3 points. And actually get ourselves wrapped around the idea of why 3 points are necessary even. Think about it like this. 3 points determine 2 vectors, correct? In other words, I can sort of put 3 points together as long as I share an initial point, and there's 2 vectors, one and the other one. Well, 2 vectors by themselves, we can always get a vector normal to both, right, with the cross product of them. So if we know the cross product of 2 vectors, Then we have a vector normal. Well, points on these are easy to come by. So we have a point, a vector normal, we're done. So that is why we need 3 points for a plane and not less. Let's do an example. In fact, we'll use a 3-point example here. So find an equation for the plane through the following 3 points. P is going to be 1, 1, 2. We'll let Q be 0, 1, negative 1. And R will be 1, 2, negative 1 as such. There's our 3 points. Want the equation through that plane. So again, these 3 points, if you put them with a common initial point, as in one of these points is the initial point of the other two, we can have 2 vectors and get the cross product. All right. So say, for example, this is not going to be accurate as far as where the spatial locations are, but say we put P in the middle. So say there's P. Say we stuck Q over there and R over there, right? So suppose this is how things work. And again, the spatial orientation doesn't matter to us. I don't care really. Then the vector we need, PQ cross PR, would be a fine normal vector, right? Because it's orthogonal to both those vectors. But also, if I'd put Q in the middle of this, for example, I could have used something else. So I mean, you don't have to be married to PQ cross QR, or cross PR, excuse me. Had you had Q there, you could have done QP cross QR. So it doesn't make a difference, but this is fine. Okay, so we need to get PQ, we need to get PR, and we need to cross them. So PQ, let's see here. So we've got negative 1 and 0 and negative 3. So negative 1, 0, and negative 3. PR, right, is 0, and 2 minus 1 is 1, and negative 1 minus 2 is negative 3. So that should give us 0, 1, and negative 3, like that. And let's see here, PQ cross PR. I'm not going to go through the full calculation this time, but I will give the determinant, and in theory my notes are correct, so hopefully this will be the right answer. Negative 1, 0, that should be a negative 1. Negative 1, 0, negative 3, and that should be a 0, a 1, and a positive 3. There's your determinant. Okay. If you work through that, you get 3i minus 3j minus k, and there is your normal vector. So there's your normal vector right there. Okay. Well, we need a point and a vector normal, so we got plenty of points to pick from. P, Q, or R all work. Let me come over here and continue working. So any point will do. I don't know. I like P, but if your name starts with Q, you can use Q if you want. So any point will do as our P naught. And let's see here. We want, so here's our equation. It's AX plus BY plus CZ equals D. And remember, D was that ugly looking thing that's just a big constant. And now we have all these values because the coefficients over here are the components of the normal vector. And the x naught, y naught, and z naught are the values of the coordinates here. Okay? So I plug in. Normal vector is 3x minus 3y minus z equals, and then 3 times 1 gives me 3 there. That's ax naught. Negative 3 times 1 gives me minus 3. And negative 1 times 2 gives me minus 2. So after all that, I get 3x minus 3y minus z equals negative 2. And there's the equation of the plane. And if you're unconfident in yourself, as sometimes I get, what's a good check? Try all these points and make sure they all work in that equation. If they all solve it accurately, then you have the right plane. Okay? All right. So there's an equation of a plane. Let's talk about two planes together and what they do. Well, if you think back, so in the very first section, I talked about what happens when you graph simultaneous equations like x equals 3 and y equals 2. Well, it's two planes and they cross in a line. Well, that's true in general of non-parallel planes. So two non-parallel planes intersect in a line, okay? And let's learn by example here. So let's find the parametric equations for the line of intersection between the following two planes, between the planes 2x plus y minus z equals 7 and x plus 3y plus z equals -1. So there's two planes. They are non-parallel. They will intersect in a line. Let's figure out what that line is. All right, so what do we need here? Well, we need equations for a line. What is a line made out of? A point and a vector parallel. So we need a vector parallel to the line, which we'll call vector v, and we need a point on the line, which we'll call p naught, and it will be x naught, y naught, and z naught. Okay? Well, a vector parallel, think about this. So let me draw my picture here first. So let's see here. Let's see if we can make up for the picture I drew in the first section that showed this and was terrible. All right, so there's one plane. And then let's have another plane sort of, let's see here. So here's the front end of it. And it's going to go, well, let's see here. So here's the front end of it, and it'll go something like that. It'll kind of stick out like that. And then the imagination of 3D here, let's cut this part off and have that plane be sort of on top, and then we'll have it come up like this and sort of come in behind there. And does that look like three planes intersecting? What am I missing here in my picture? That looks good. That, let's see here. So, and the line of intersection is going to be this line right there. Right? So this shouldn't be going in like that. So in fact, what if I outline one of the planes in black? So it'll really look great. So there's one of the planes. All right. Beautiful, beautiful 3D. All right. And so there's the line of intersection that we care about. This line right here. Line of intersection. And of course, that line will go on infinitely. So it goes on in both directions. In fact, we can even make it look like that if we want. There we go. Okay. So what do we need here? Well, we know that the line is a bunch of points common to both planes. And if that's the case, then both planes have a certain normal vector to them, right? The vector that we use to determine the plane, all right? Well, if points lie on both planes, those points are orthogonal to both normal vectors, all right? So let me come over here and say just that in words, or in written words at least. So the line of intersection is perpendicular to both planes' normal vectors, n1 and n2. In other words, they both have some normal vector, and the line is perpendicular to both of those, okay? And that means that if I want a vector that's parallel to that, well, my line is perpendicular to both of these, Well, that means I need a vector that's also perpendicular to both of these vectors. Well, what vector do we have that accomplishes that goal? The cross product, right? So therefore, n1 cross n2 is going to be parallel to the line of intersection. And that's going to be the vector we need to function as our vector v, our parallel vector, okay? So what's n1? Remember, how do we get normal vectors? We just read off the coefficients of the planes, all right? So normal vector 1 is 2i plus j minus k. Normal vector 2 is I plus 3j plus k. Okay. We need the cross product. So there's our normal vectors right there. Okay. We need the cross product. So again, I'll suffice with the details here and take a leap of faith and hope that my calculations are correct. So 2, 1, negative 1, 1, 3, and 1 is our determinant. That shouldn't be there, but you get the picture. And if all works out properly, that should give you 4i minus 3j plus 5k. Okay. And so this will be our parallel vector v. There you go. Okay. So there's our parallel vector v. All right. Well, we're halfway through. We now need a point on the line, excuse me. So we need a point common to both planes. Well, here's my plan. So I'm going to arbitrarily let x equal to 0 and solve a linear system for y and z. All right, so my plan is this. Where are my planes equations? Here we go. My planes equations are 2x plus y minus z equals 7. And the other one is x plus 3y plus z equals negative 1 as such. Well, if I let x equal to 0 here, then I get a system of equations, 2 equations and 2 unknowns. It's easy to solve. But let x equal 0, I get y minus z equals 7. Let x equals 0 over here, I get 3y plus z equals negative 1. Right? Well, I can solve this for y and z very easily. The z's cancel out. I've got 4y equals positive 6. So y is equal to 3/2. Plug that back into my equations. Plug it in here, for example. 3/2 minus, so 7 is 14/2 minus 3/2. So z is negative 11/2. Yeah, that's right. So z is negative 11/2 just by plugging y back into this equation here. Okay. So I have a point now, 0, 3/2, negative 11/2, common to both planes. Okay. All right. So now, well, I'm essentially done because now I can parameterize the line. L has parameterization. Remember how the equations of a line worked? It was always x naught plus tv. Well, so let's see here. Where am I? So this is 0 plus 4t, x equals 4t. Y is equal to, so we have 3/2 minus 3t. That's right. And then z is equal to, there's negative 11/2 plus 5t. And there's the parameterization for the line of intersection between these two planes. Okay, so that's line of intersection. Let's talk about point of intersection between a line and a plane. Let's get rid of all of this. Give ourselves fresh space to work. Okay. Example. Let's find the point of intersection between the line x equals 2 plus t, y equals 1/2 minus t, z equals 3t, and the plane x plus 3y minus 2z equals 1, right? So we want to find the point of intersection here. Okay, well, what are we going to do? Well, every point on the line has coordinates given by these parametric equations. So the point 2 plus t, 1/2 minus t, and 3t lies on the plane x plus 3y minus 2z equals 1, exactly when the points on the line satisfy the planar equation. Okay? When the following is true. When 2 plus t plus 3 times 1/2 minus t minus 2 times t minus 2 times 3t, excuse me, 2 times 3t equal 1. So when the coordinates of the point satisfy the planar equation, the point is on the plane. Okay? Well, algebra here is not horrible. Minus 3t, a minus 6t equals 1. This is an equation in a single variable. Let's see here. So we have negative 9t and positive t is a negative 8t. This is 4/2 and 3/2 is 7/2. So we can scoot that over to the other side. This is 2/2 minus 7/2 is negative 5/2. And so t is equal to positive 5/16. Okay? That's the t value that corresponds to the point on the line. The point itself, though, got to plug this back into the linear equation. All right? So when t equals 5/16, x is equal to, what is this here? This is 16/16 plus 5/16 is 31/16. 1/2, that's 8/16 minus 5/16 is 3/16. That's y, excuse me. Y is equal to 3/16. And 3 times 5/16 is 15/16. And so the point of intersection is 30, why do I have 37 here? Should be 31. Is that right? 32 plus 5. No, it should be 37, yes. Because 32/16 plus 5/16. Yeah, that looks right. 3/16 and 15/16. Is that what I got? Yes. And so this is the point of intersection. Okay? So, there you go. All right. One more topic here to discuss in this section. The distance from a point to a plane. Distance from a point to a plane. Distance from point to a plane. Okay. So, okay, let me draw the picture first, and then I'll go through the verbiage. In fact, let me draw it lower. I don't get caught running into my own writing. All right, there's a plane. Okay, here's a point, S, not on the plane. And we want to know how far is it from S to this plane. Okay, so here's a point on the plane that we know. right? To know a plane, we must know a point, we must know a normal vector. So here's the normal vector. There's n, right? Well, I don't care how far it is from S to the known point P. That's not my question. My question is how far is it from S to the plane? So whatever point we get to first is the right point to pick, right? In other words, we don't want to go all the way over here. When this plane goes on forever, we can just drop straight down here, right? Think about it like this. This point, the shortest way to get down to it is just to fall straight down. The plane goes on forever, right? So the plane really extends on and on forever and ever. And so why would we want to go all the way down here? Well, if we just drop, we'll land right there, and that's going to be the shortest distance, not the hypotenuse of some triangle, right? Okay. So what do I want to figure out here? Well, I want to know how far is it from, well, in fact, let me draw it. Yeah, that's fine. So I want to know how far is it from the point S to the normal vector. All right? So I want to look like that. And so let's see here. So this is going to be that extension. I want to draw this differently. Yeah, let's draw it a little differently here to make this very clear what's happening. So what we'll do is we'll just sort of, we'll drop down that. So that's the distance that we care about here, right? So this is going to be the landing point down here. There we go, that looks better. And then something like that, right? And then that's a 90-degree angle. So let me put some words up here and make this clear. So for a plane with normal vector n containing point P, the distance d from any point S to the plane is the length of the vector projection PS onto n. So let's see. Do I want to draw this differently? No, it's okay. Yeah. So what I want over here, I want this distance here, right? So it's the same distance as over here. It just happens to be on this side because this is where my point P is. So I want this distance, which is that distance, right? That's what I want, the vertical distance from the point dropping down to the plane, right? So this is D, and this is the length of proj sub n PS, right? The length of the vector projection of PS onto n. Because here's vector PS. We're dropping this perpendicular down from PS to n, and that vertical length, same thing as over here, is the length of that projection vector, okay? All right, so what is that then? Well, think back to the dot product section when we talked about the length of the projection. Well, remember that probably the easiest way to write this would be the length of PS dot n over the length of n, like that, right? So the length of this vector, which is PS dot n, over the length of n. And in fact, it's worth noting, we had a name for this even, was the scalar component of PS in the direction of n, right? So we had a name for that thing. And that's the length that we seek, okay? Well, after all of that stuff, let's do an example of it and see how it works in practice as opposed to theory. So let me get rid of this. We'll leave our picture up there just to guide us through this. So let's find the distance I should say from, not between really, but the distance from the point S, which is 1 to -1, to the plane 2x minus 2y plus z equals 4. Okay. So again, what we need here is two things: a point in the plane and the vector n, the normal vector, right? So we need p, we need n, and we can get that distance. All right. Well, point in the plane is easy to find. Any point works. You may as well find the intercepts, though. So any point in plane works. Probably the intercepts are going to be easiest. Where does the plane cross the axis? Cross one of the axes. So if we let x equal 0, we let y equal 0, well, what is z? It's 4. So this thing has z-intercept 0, 0, 4. It crosses the z-axis at 0, 0, 4. So we'll let p equal to 0.004. All right. N, let's see here. N comes directly from the coefficients of the planar equation. Is that what I've got here? Yes. I've got 2i minus 2j plus k. Yeah, that's right. And the length of n is, 4 and 4 and 1 is 9. So length of n is root 9, which is 3. Good. Okay, great. Now we need vector ps. So I'll scoot over here. Vector ps. Oh, where's s and p? So what do we got? 1 minus 0 is 1. And 2 minus 0 is 2. And -1 minus 4 is -5. Right? That vector ps, yes it is, good. So we now do ps dot n over the length of n. Ps dot n is what, 1 plus 2, or 1 times 2 is 2, plus -4 is -2, and plus -5 is -7. Is that what I've got? Yeah. So this should be -7/3. And let's see here. So, and we need the absolute value of that. So d is equal to the absolute value of -7/3, which is 7/3. So there is your distance from point S to this plane. Okay, that's it for lines and planes in 3 space.